What does JCB know about speed?
The fastest man on the planet. No, not that one. That one. Behind the wheel, 1,600 horsepower. Utah, USA, where only he has been before. But this time, it's different. This time, it's faster. This time, it's hydrogen.
Hi and welcome. We're at RAF Wittering today. We're doing our testing of our Hydromax land speed record car right now. At JCB, we're a family-owned business. Lord Bamford, our chairman, owns and runs JCB, and he's absolutely passionate about hydrogen, but he's also passionate about innovation.
Bless him, you know, the chairman's either completely mad or totally brilliant, but he's just willing to ride with that, and the rest of us to go, yeah, all right, we'll give it our very best shot, see if we can make that happen. And based on what I've seen so far, we will.
At JCB, we say that innovation is our lifeblood, and it's amazing to be a part of events just like this, where we're proving out just how innovative JCB can be.
JCB has a pedigree of speed attempts and records. So back in 2006, we did our Dieselmax car, which reached 350 miles an hour in Bonneville using 2 diesel production engines. We've also, as a company, developed the world's fastest tractor, and we took it up to over 135 miles an hour. And we've also got our GT backhoe, our dragster, taking our backhoe to unprecedented speeds as well. So we know a thing or two about speed, and it's perhaps unusual as a construction company where our machines normally operate at relatively low, safe speeds on site to be going for speed. But we do speed because we learn and we develop. That learning carried across to our hydrogen development. The learning from the Dieselmax land speed record car has then carried over to the Hydromax car as well. 20 years ago, in 2006, with our Dieselmax car, we were proving this was the first time that JCB had diesel engines produced, designed and produced in-house. We took those diesel engines, we put them in a car to prove that they were robust, reliable and could perform for our customers. And it's just the same 20 years later. We have a brand new hydrogen engine. We're putting 2 of those into our Hydromax car to prove that the hydrogen engine technology can perform for our customers. It's so important that we can prove that the internal combustion engine technology has a future. It's got a long future ahead of it in a zero emissions world. Back when we started the hydrogen program, we were being told that the engine's days were numbered. What we're here to say is, actually, the hydrogen engine technology is a way that we can use this technology going into the future while giving our customers everything that they still need from their machines. JCB is a pioneer in hydrogen technology. When we started the hydrogen program, we were one of only 3 companies in the world looking at it. Now, most truck manufacturers, most automotive companies, most of our competitors are looking at hydrogen technology. JCB are not only early adopters of hydrogen fuel, but we're innovators in that hydrogen fuel. We're the first to have our hydrogen engine certified. We've done over 50,000 hours worth of testing. And we're also the first now to have our hydrogen machines launched commercially with customers in the real world, doing real jobs right now. JCB are record breakers. JCB are history makers.
There's still a lot of work to do, and the boys and girls over there who are working on the car right now, we've had about 3 hours sleep overnight because there was a lot to do yesterday and a lot to do today. They know just how much work there is to do. The fact that they are so good at what they do means that we have not just got a fighting chance, we've got a brilliant chance of doing it. Can't wait to start.
We obviously announced this to the world last month that we were doing this. Really, what you're seeing here is a lot of activity that's gone on for more than a year. We actually kicked this project off properly in spring last year, and the very first meeting where we got everybody together to really work out how we were going to do it was actually on the 5th of June 2025. So just a year later, we've gone from that initial brief and that initial design sit down to running the car here at Wittering. So it's all about test. That's what we're doing. We gather lots of data. The car has got a fantastic telemetry system on it, data gathering system on it. You'll see a little bit more of that later when you get a chance to go and see the car and get a bit up close and personal with it. and talk to some of the technical team. So that harvests that data, and that allows us to make sure that we are happy with all the subsystems that are working on the car. So it's a complicated animal. It's got lots of interacting subsystems. We've got a fuel system. We've got the engines, of course, the gearboxes, braking system, safety system, parachutes. All has to work together faultlessly, and that's what we're here to do. So it's very much test, find a problem, fix a problem, test, get some data, correlate that back to our models and predictions. And we're steadily building up the speed as we build that confidence. So in the last week and a half that we've been here, we've unloaded the car, we've commissioned the car, got it up and running. We've done several runs now, tail end of last week and into this week. And we'll be doing numerous runs through today, tomorrow, and all the way to the end of the week. As I say, slowly sort of building up that confidence in all the systems in the car. Really, what that allows us to do then is decommission the car at the end of the week. It will go back to ProDrive. There's some more modifications it will make, some more software changes, some more hardware changes. And then the car gets packed up and shipped out to the US at the beginning of July, and then we'll follow it out there for recommissioning. And then we do FCTA Speed Week, first week of August, and FIA World Land Speed Record in the second week of August over in the US.
The road to zero was born out of the automotive world, about getting to net zero, about getting to zero emissions. At JCB, we're a bit different and we think a bit different. And really, that's where we see it as the off-road to zero. Because even though our machines have 4 rubber tyres and a steering wheel, our machines are very different to the automotive world. Fundamentally, our machines are work tools. They're designed to do a job. They're designed to dig a hole, move pallets around, build houses, as we'll get on to. And fundamentally, really, that's what we think about at JCB all the time. We are a very customer-centric company, and it's all about what our customers do with the machines. So today, that's building regular infrastructure. So that's building schools, roads, hospitals, railways, airports, and homes. And there's a whole load more infrastructure to build, both in the UK and in other places around the world. So there's a huge, huge investment ongoing in terms of developing those machines, so developing those projects. But actually, we've also then got a future infrastructure we've got to think about. So you've got to think about wind farms, solar farms, nuclear power stations, hydrogen pipelines. We've got to be able to both build that existing infrastructure and then also build these new infrastructure. And it's that new infrastructure that we call clean energy. And it's that same clean energy that's then going to power our machines in the future. So there's 2 ways really we can do this. So one for the open job site is that we can use grid electricity where we have access to grid power. We can use electric machines with batteries. And typically we see those as compact machines. Why is that? Well, because they are repairing and maintaining existing infrastructure. They're repairing pipes and cables under the ground. They may be doing extension digs and that kind of thing. But the challenge is, what do you do for anything else? So the remote job site. So for that, we need an alternative fuel. Today on construction sites, we bring diesel, we bring the energy to the site. So we have to do that in the future as well. And so we've got our remote job sites, and I've got a picture here of mountains and trees, but actually remote for us is anything that doesn't have that grid connection. So that could be an RAF base here, that could be a house building site just on the edge of the city. At JCB, we provide the machines that build that infrastructure and put that infrastructure in for the first time. So when we come to site, we have to bring the energy with us. And really that then gives us our portfolio. So we've got compact electric machines, but for larger machines, we need that alternative fuel to get the machines working. So diesel's what powers JCB machines today. And actually we realized diesel's fantastic. You know, it's transportable, it's energy dense, it's low hazard. You can put it in a jerry can or you could put it in a 40-ton tanker. It's brilliant for moving energy around, and that's why we use it on site today. But obviously the challenge is it's a fossil fuel, produces CO2, causes climate change. So we've got to find a different way of doing things. So the next step really is looking at biofuels, so biodiesels and HVO. So HVO stands for hydrotreated vegetable oil. So these are oils made from waste oils and fats. So you take waste chick fat, for instance, and then you put it through a number of industrial processes. It's a drop-in fuel. So HVO is a drop-in fuel, and actually all JCB machines from 2016 onwards with a JCB engine can run on HVO as a drop-in fuel. So you can mix it in with the fossil diesel, or you can run it as a standalone. We've now also more recently done a B100 biodiesel fuel pack. So this is run on a less refined form of biodiesel. Typically, if you see, as you're driving along the road, a truck which says I'm powered by chip fat, that's typically your biodiesel, your B100. Essentially, it's a less refined form, so it can suffer from things like diesel bug, gumming up in the winter from water absorption. So we can do that on some of our large excavators. It does require a machine modification and additional servicing, but we can do that. And that really provides our customers with a short-term solution to reduce their CO2, not from the tailpipe, but from the production process. The main challenge with biodiesels and biofuels is where the fuel comes from. So the challenge really is on sustainability. If you know you're getting it from the local chippy, that's absolutely fine. But really, we've just got to be careful that it's not coming from supply sources where we're causing deforestation through palm oil and that kind of thing. So then the next step is, how do we go to zero carbon? How do we take carbon out of the equation altogether? So we talk about electricity, so made from wind, solar, nuclear. It can be made on site, it can be made on a farm, it can be made locally. But the challenge is it's hard to move around and it's expensive to store over long periods of time. And so really that's what led us to hydrogen. What we're trying to do really is just bottle sunlight and bottle wind energy and turn it into a form that we can transport to site easily, that we can refuel quickly and use in a similar way to diesel. And that's really what hydrogen gives us. So the first projects that we then did on hydrogen with the technology that we had available to us was then fuel cell technology. The first challenge we have with the fuel cell is really the transient power demand. So fuel cells, if you know anything about them, they like to run in a very steady state condition, very low power, very steady state. The challenge with our machines is that we run very transient demand. What that means is that a JCB excavator like this can go from zero load in the air, full load, almost instantaneously. It then digs a bucket of earth out, it dumps it, and back again every 27 seconds. It's doing this dig cycle. What that means is that the fuel cell can't cope with that. We have to then supplement it with power batteries that are doing this charge and discharge cycle. We've also got to have complex electronic systems which are telling the machine where the power needs to go, whether it needs to go direct to the system, or whether it needs to go into the batteries to charge them. So fundamentally, we've already got a machine that's far more complicated, far different to a traditional machine we've got today. But the other side of it that nobody told us about is when there's three things that fuel cells don't like: dirt, dust, and fumes. And that's a real hazard of the job in the construction industry. So we've had cases where somebody's running a fuel cell power generator next to a diesel power generator, and the fumes from the diesel power generator poison the fuel cell that's standing next to it because of the VOCs that get into the fuel cell. And then finally, really, and I could talk for a long time on this machine, I'm not going to, but just to kind of, I guess, explain the journey we've been on in terms of the technology, there's a big unknown in this machine, which is the lifetime of the machine. How long is how long is this equipment going to last in the field? And with these machines, they don't just have a first life, they have a second life, third life, fourth life. These machines, they might start life in the UK, but they could go anywhere in the world. So we've got to make sure our machine can work just as well in the Arctic Circle as they can in the Sahara Desert. So the question really is, after its first life, who's going to buy it? Who's going to buy it as it is? Are they going to want new fuel cells? Are they going to want new power batteries? And then the other thing is that on the robustness of the system, these machines, there's a few little things about them. So the coolant that goes through the fuel cell can't conduct electricity because it's an electrical device. So where on a normal machine, the coolant costs £2 a litre, on this machine it costs £56 a litre. The engineers refer to it as whiskey. So it's the same price as a bottle of good malt whiskey. It doesn't taste as good though. But the challenge really is that, well, how does this work in the field? It's not uncommon for a coolant pipe to burst or pop off in the field. What people would normally do is you put it back on, get a bit of tape, get a bit of water from wherever you can, you fill it up, you get it back to the yard and do the fix. If you do that on this machine, you short-circuited your £100,000 fuel cell. The whole thing's scrapped, the whole thing's stuck in the field, and you've now got to recover it. So there's some big challenges that, again, as engineers, we can do anything. This is the most technologically advanced machine we've ever built. And it's fantastic for the engineers that were working on it. But is it practical? Is it cost effective? Is it going to work in the real world? Now, fundamentally, after the program, it's a bit bittersweet. The most technologically advanced machine we've ever built, but also the most expensive. most complicated, and the least robust machine really built. Now, JCB customers, they're fairly frank with us, and they say we can design whatever machine we want, but it can't be too expensive, it can't be too complicated. I think we achieved that with this machine. And so really, and so this was back in 2020, we developed this machine. We've still got it up and running. Well, I say up and running, we've still got it up at our test site. It's not running at the moment. Unfortunately, the power batteries let us down. And now the battery supply won't work with us because we killed the batteries too many times. But it serves as a great point on our journey of technology. And so then it was back in the summer of 2020, 20th of July 2020, in our power systems division, our engine factory, that we met with Lord Bamford, JCB's chairman. And we explained the electric machines. We said, they're great on the compact side, but as you scale up, there's nowhere to charge them. We explained the fuel cell technology. We said, we love the hydrogen. The hydrogen is great, the fast refueling, the fact that you can store energy on the machine. But the challenge is we just don't like the technology. And sat in the engine factory, Lord Bamford said, well, why don't we just do an engine? And if we're honest, we had looked at hydrogen engines. We typed them into Google to see about them. And everything that we read told us not to do them. And Mark will take you through in our engine station later exactly what that learning was on that hydrogen engine. But fundamentally, it comes down to three things. When we come to our hydrogen engine, and what we've done really with our hydrogen engine technology, and we've pioneered it, we are the first in the industry to work on hydrogen engines, to have them certified. We've done over 50,000 hours worth of testing on our hydrogen engines. But the first thing that we wanted to achieve with our hydrogen engine is actually, number one, is emulate a fuel cell. What we liked about the fuel cell, probably the only thing we liked about a fuel cell, so we put zero carbon fuel in, we get clean steam out. But the other side of our hydrogen engine technology is that we want to match the existing technology. We want the same power, the same torque, the same performance as the diesel engine, so that when we're building machines on our assembly line, as I said, we've got 350 different product models. We want to be able to build a diesel machine, and then we build a hydrogen machine straight after. We just have a different engine that goes in a different fuel tank. And finally, we want an identical operator experience. We want somebody to be able to jump off a diesel machine, jump onto a hydrogen machine, and perform in exactly the same way. As I said, in our industry, in our world, our customers just want machines that do a job. I was fortunate enough that in the early days of doing our hydrogen trials on site with our machines, I spoke to all the site operators, the site managers, and they said to me, and they were very, very clear with me, I know you love your diggers, but we don't. We love building things. Your machines are fundamentally here to do the job. Is the machine going to do the job on site? That's the most important thing for our customers. The other side of it is then having familiar refueling. Today, diesel machines can be refueled in a matter of minutes. We need the same for our hydrogen machines. And then finally, servicing and maintenance. These machines could go anywhere in the world, so we need to be able to maintain them and service them anywhere in the world. And really, over the course of 5-6 years that we've been working on this program, that's what we've achieved. Again, as Mark will take you through later in the station. It's not just about the engine, it's about the machine as well. So we're now at a point at JCB where we've now launched 2 hydrogen machines. This is our first machine, our G60 RSH hydrogen power generating. So this is just like a diesel generator, but rather than have a diesel engine in it, we've got a hydrogen engine. So this is providing electrical power, clean electrical power on site, providing that power that we need to then run marquees like this today. What we're also doing though is combining it with technology. So one thing we've learned with the battery technology is, and this is a great application where a hybrid solution works really well. So we've got our hydrogen engine battery pack, our power pack solution. So this is essentially a box full of batteries. And what we do is that actually we power the site off the batteries. And we've turned our hydrogen generator into a battery charger. So what we do is that the site runs on the batteries. As the battery capacity drops, we get to a threshold. We then turn the generator on. That adds a battery charger. It charges up the battery back to full and then switches off again. The reason why we're doing this is that typically on a construction site, diesel generators are often sized for peak power application. Now, that may be seen once a month. That may never be seen at all. And in reality, most of the diesel generators are running at around 10% load, charging laptops or running kettles and microwaves, fridges. So and that's a very inefficient load point for an engine. So what we're doing here is instead of running at 10% load, we run at 90% load, 100% load to run our engine at the most efficient point, use the least amount of fuel, and then charge our batteries, and then we switch the generator off. So we're reducing hours as well. So you see, it's a known machine architecture, it's robust, reliable, and serviceable, and it's a hybrid system. And this is really our product we're best known for around the world, our 3CX hydrogen backhoe loader. And we've got one or a couple to show you here today as well. So fundamentally, with this machine, compared to the fuel cell, which was a complete rip-up of the architecture, this machine is essentially the same as the diesel. The difference is, instead of a diesel engine, we've got a hydrogen engine. Instead of a diesel tank, we now have hydrogen tanks on the roof, which we'll go through later in another station. So there's minimal machine change. It's robust, reliable, serviceable, can be used anywhere around the world. And fundamentally, it gives that level of affordability and adaptability into the market. What we're trying to do is provide zero emissions, net zero, with zero fuss on site. And actually, after 5 minutes of people getting very excited when these machines are on site, actually they just blend in. They're just normal. If this machine was yellow and this engine was black, you wouldn't know the difference. Fundamentally, it's just what's coming out of the tailpipe. We've changed the equation. You don't put carbon in the fuel tank, you don't get carbon out. So those are two hydrogen machines that we've got now. They're commercially available. They're working with customers around the world already today. And really, we're at step one of that journey. We've just started, but really we see the future's bright for those machines going out to the field. So that's really a basic kind of, I guess, a fundamental understanding of why we're doing what we're doing, why we're doing that engine technology. And hopefully what you'll see today is that actually a lot of what we've covered here actually all gets built into the Hydromax car. In a similar way to our machines, the Hydromax car is an evolution of the Dieselmax car. Yes, we've changed every component, and we've touched every one and looked at every single one, but fundamentally the architecture is the same, the technology is the same, it's a different engine, it's a different fuel type. You'll see today and through the work that we're doing, it's not the poor piece of metal's fault, it's what you put in it. If you put a zero carbon fuel in, you get zero carbon out of the tailpipe. And really we see a bright and long future for the internal combustion engine.
Behind me now is our hydrogen 3CX backhoe loader. So this is a machine that we've been developing for the last 5 years. It's now in production, on sale. It is a fully complete machine. It is not a prototype. This is real world. And this machine ultimately is based very heavily on our diesel 3CX machine that many people know and love already. The key differences ultimately obviously are, where previously we've had a diesel-fueled internal combustion engine, we now have hydrogen. And that hydrogen is stored in the form of compressed gas, where we have it in 3 tanks on the roof. The main thing with the machine is that we've minimized the amount of change. It's not reinventing the wheel. We're using robust, reliable components, which are serviceable as well. And ultimately, it's a solution that is affordable and adoptable. That's our goal with this project. So if we take a look at the actual fuel system itself. So, like I said, on the roof, we've got 3 tanks. So these are aluminium cylinders, and they're wrapped in carbon fiber for extra strength. So they store pressure at 350 bar pressure to package about 9 kilograms of hydrogen on board. So these cylinders have been through rigorous highway approval. So they go through impact testing, fire testing, a whole world of various different arduous tests. And then we've gone and taken them and put them on the roof of our machine now. So from there, the gas then we're controlled by 3 valves on the end, where it flows out, down the A-pillar here, and through onto the fuel rail, where it is burned just like any other fuel in an internal combustion engine. Obviously, the key benefit here is zero carbon going in, there's zero carbon coming out. That's the key thing here. You've got water coming out the tailpipe. If we look at Hydromax, so this is a cutaway we've got here. So actually, you see this is where the driver sits on JCB Hydromax and cockpit area here. And immediately behind that, we've designed a fuel system for this car now, which comprises 2 of these cylinders here. So just like how we've got carbon fiber wrapped cylinders here, we're using the same technology. So there's a type 4 cylinder where we've got 2 of them on board. We store about 4 kilograms of hydrogen on board there. And that's been sized ultimately for the length of run that we will require when we're out in Bonneville. So it's a 700 bar system, so it's twice the pressure ultimately of what we're running here. And the reason for that is that because of the packaging challenges and the packaging envelope that we want on the car, we've had to shrink this fuel system down to, you can see it fits. So we've got driver compartment here, rear engine, and we've got an ice tank above as well. So it's a really narrow packaging envelope. So that's where we've gone to that technology instead. Nice. And ultimately then, when the fuel is stored in that fuel compartment, it is then separated out into each engine. So it has separate fuel lines running down and supplying both engines, front and rear, simultaneously. In terms of refueling, so if I show you this here, so actually, if I take this refueler here, you see we have a standard 350 bar connection nozzle. And on our machines like this, we have filling receptacle, and it's a simple case of push fit to connect. We then go to the refueler, press a one-button operation to start the refuel, and this will cause gas to flow from the refueler to the machine, and it can fill this in 10 to 15 minutes from 0 to full. You get another full day's shift out of it again. Okay. The principle is exactly the same with Hydromax. We've actually been using this refueler for our earlier running of earlier this week and last week to supply the car for the runs that we need. The connection is the same. We can use the common interface, again, because we're using automotive grade components throughout.
With the hydrogen combustion engine, we were aiming for 0 carbon in, clean steam out. So we're trying to emulate a fuel cell's performance, but with the hydrogen combustion engine. We developed that over the last 5 years, and we've actually got an engine now which delivers the same power, it delivers the same torque, and it also delivers the same reliability as its diesel counterpart, but doing that without the carbon. And what that gives us is an engine which, when it's in the machine, from the operator perspective, it has the same performance characteristics. Whether you're lifting up a pallet of bricks or you're going into the pile to excavate the earth, the operator in the cab has the same experience. And also, the people who maintain our product in the field, our service engineers, come in their van, service the product on site, and it's very familiar territory because it's an engine. It's easy to make a hydrogen engine run. It's difficult to make one run well. And by run well, I mean one that can do tens of thousands of hours operating in a very arduous off-highway environment. When we look at our diesel engine strategy, so, 20 years ago, just over, JCB started moving into making its own diesel engines, displacing some of the competitive engines used in our product at that moment in time. So when we look at our modern diesel engines, we are forced air induction, so we're not naturally aspirated. We have direct injection. So direct injection means that the fuel, the diesel, is held in a rail, quite high pressure, around 2,000 bar. We then inject it into the engine. And when we think of diesel combustion, we rely on the piston coming up, compressing the air until it gets to a very high temperature. The fuel then is injected in, and it's the temperature of the air which causes the fuel to ignite in a diesel engine, a compression ignition engine. So we have the fuel, the air, the fuel, we mix that. Again, we go for high temperature combustion. That allows us to extract on the diesel engine the maximum amount of energy out of the fuel as we go through. But because we're doing that on our modern stage 5 diesel engines, we have to have quite complex after treatment, SCR, a DPF, AdBlue, to control the engine's emissions out of that. But modern diesel engines are very efficient, 39–40% brake thermal efficiency. A lot of people forget that with our diesel engines. But importantly, they give the product the instant torque and power requirements that are very different from automotive. So our machines, this is a 4.8 litre engine, a 4-cylinder engine, large displacement. But when a backhoe or goes into a pile, you go from no load to full load as you're trying to break the earth out. Massive hydraulic load put on the engine. The engine can't bog down. That's the real difference of how our engines operate in an off-highway environment. We go from basically moving from a liquid diesel, into a gaseous fuel, which is hydrogen. Now, hydrogen compared to diesel, if you remember, with diesel, we rely on compression ignition. With hydrogen, we use a spark plug to ignite the fuel. So these engines here, so just to be clear, this is the engine that's the 55 kilowatt, 74 horsepower engine. We have the fuel that's put in. We then mix it to get a good mix. But because the fuel is easily ignitable with hydrogen, we don't need much energy, but we have a spark plug to then ignite the fuel. And it's low energy to ignite the fuel as well. Now, hydrogen by weight if I have a kilogram of hydrogen in my hand here, it's the same energy equivalent of 3.3 litres of diesel. So by weight, that's that. So in our hydrogen engine, we're actually injecting a small amount of fuel, but because the energy in the fuel is quite high, that's why we can get the same power and torque out of the hydrogen engine as we can with the diesel engine. So there's no difference at those power levels. So when we break down our hydrogen combustion engine, again, 55 kilowatts, 74 horsepower, we have turbocharged. So you go back to the early engines, naturally aspirated conversions. We've got a brand new boosting strategy on the engine. The air then is mixed through the intake manifold, and this engine is what's called a Hort fuel injected engine. So this is DI with diesel, direct injection. We have port fuel injection, and you'll see an animation of that. That allows us to have the fuel in the fuel rail at about 10 bar pressure. We then inject the fuel through the port injection into the intake manifold, and then through down into the valve. The charge then goes into cylinder where we complete the mixing. And you'll notice here, this previously had high temperature combustion. With hydrogen, we're focusing on what's called low temperature combustion. The reason we do that is instantly you think, well, low temperature means low power. But going back to what I said earlier, because of the energy density of the fuel compared to diesel by weight, we can have a lower temperature combustion because of the higher flammability range. When it ignites, that gives us the same power stroke of the piston moving down and obviously turning into rotational movement of the crankshaft. So we're getting low temperature combustion. And because we're doing that and controlling the emissions, we've got this engine to stage 5. This engine is certified to stage 5, type approved across Europe. We're doing all of that and we don't need conventional after treatment. So there's no DOC, there's no DPF, there's no SCR, there's no AdBlue on this engine. So we can put this engine in a digger, sell it today to the strictest emission standards in the UK and Europe, and we can do that without the conventional after treatment, which is a great win for us. And it's really demonstrating how clean the engine is. Everybody told us at the start of the programme, you cannot get hydrogen combustion engines to those efficiencies, but we have done. And we get the same performance out of that product as well.
So we've just done run 14, so 14th run here at Wittering. We achieved a speed of 177 miles an hour, so 177 miles an hour. Car was fitted with calibrations to 350 horsepower per engine, so a combined 700 horsepower. We're only using the first three gears. First three gears, all successful, satisfactory. So simply just walk you through what we just did. We've got the car ready to go out. Filled it with gas to 350 bar, so that's about half the pressure that we'll run in the US when we do the land speed record. Got the car ready for a push. Now, we then noticed a coolant depressurization issue on the front coolant tank. We tried to fix it on the track, we were unsuccessful, pulled it back into the garage, made the fix, repressure tested it, got it back out to do the run. So we started the run, got it ready in front of the push vehicle, in front of the Land Rover, did a push to about 45 miles an hour. That allows us to get the clutches to engage. You're in first gear already, clutch is open. As you push, a 45 mile an hour, clutches engage, and then Hydromax takes it up from there. And then Andy accelerates away from the push vehicle, which you would have seen as you came past here. Through first gear, shift point at 3,900 RPM. So we're short shifting at the moment. We'll extend that over the next few runs to increase that shift point all the way up to about 4,300 RPM. So shift at 3.9, into second, back on the power, again, up to 3.9, shift, pull into third. That allowed Andy to get to that 177, and then you probably would have seen parachutes deploy just as we went past the marker boards towards the end of the track. Parachute deployment and friction brakes, nice controlled stop all the way, Andy communicating with us. So a brilliant run, everything went to plan. Despite those hiccups, get to allow us to get going. And the next run now that we'll do in probably about an hour, so we're just pulling the car back into the garage. We're going to make some more calibration changes, change some of the sampling frequency on some of the sensors to jack that up a bit, change the shift point on the engines, and then get back out this evening to do another run. Similar speed, maybe a little faster, we'll see.
Okay, plan was, if you haven't already covered it up already, we are working up towards 200 miles an hour, which is as fast as we comfortably can go here, given the acceleration and braking distance, and gradually winding the wick up on the engines. So we're starting from last week with a car that had never run before, actually hadn't had both engines running in the car before, through to the end of this week, where we've got a car that reliably, consistently can start, accelerate up to the limiting speed for this 1.5 mile strip, and then slow down again safely to a stop using brakes, steering, parachutes, etc. And we're most of the way through that. So today, the engine calibration 350 horsepower-ish. As I'm learning, hydrogen engines are slightly more complicated than the average, because you've got the rail pressure, which is the actual the ejection pressure that the ejectors see, which we were running at 30 bar today, I think. Is anybody going to disagree with me? I must be, yeah. Thumbs up from the engineer at the back, that words. So 30 bar rail pressure, that is against the 50 bar we will be running in Bonneville, so we are working up to that. There is also the ignition timing. We're still not quite on full beans ignition timing while we refine and test the water injection, which is what's essential to stop the pre-ignition in the engine, because hydrogen is quite an excitable little molecule, and we need to make sure it burns in a consistent fashion rather than a massively explosive fashion while it's developing its 800 horsepower in a JCB digger engine. So all of that is in progress. To summarise then, 2 engines delivering 300-ish horsepower today. From the push start, which you saw in the distance, the Land Rover Opta is pushing fairly hard, and still at about 45 miles an hour. Once we've reached the gearing for idle speed in Hydromax, it drops the clutch, then gives me full throttle authority. The engines then start to come on boost, and we just leave the Opta for dead. Despite the fact it's a V8 monster, it's now in the dust as Hydromax sets off into the distance. Up to 3,900 RPM, which was the RPM limit we're working today, and we'll be taking slightly more on the next run, but gradually increasing the RPM limit up towards the maximum 4.5. So 3,900 RPM, and we're also just refining the change lights, the beep, and all the other indications with the intention I can hit that exactly every single time. Apparently I was 3,400 and something this time. But as I discussed with the software engineer, there's a slight mismatch between the beep and the arrow. His logic was the beep's first to warn me that the arrow's about to line up. And I said, yeah, I know, but they're still mismatched. I noticed they're about 50 RPM out. It does make a difference. So we're down to those sorts of margins in controlling the car, which is brilliant. So to 3,900 RPM in first gear, which is a little over 100 miles an hour. It's about 100 and never do sums in public. About 110, 115. Then change up to second gear, again up to 3,900 RPM, change up to third gear. When you're thinking about 2 big engines, the JCB clutches and the 2 gearboxes all need to be synchronized to within a few milliseconds to make all of that happen. And that's now happening seamlessly. So another huge result for today. The aim was to get somewhere close to the 200 miles an hour. We actually got to just shy of 180 for a couple of reasons. First of all, with all of you lovely people present, I wanted to make sure I had plenty of stopping distance so I didn't do anything embarrassing. So I lifted a little early, and also we're not quite developing that 350 horsepower yet, while we just gradually tweak up the engine parameters. So around 180 is what you saw. Lift, go on to the brakes initially. It's a 2-pedal car, the clutches are automatic. So initially onto the brake. That's because if the parachute fails, everything's happening so quickly that I should have been on the brake 2 seconds ago. So we start braking, punch the parachute blooms, and I can ease off on the brakes and let the parachute do a fair chunk of the work. And then the aim is during the last sort of 50 miles an hour also to slow the car down fairly rapidly to a stop, just so we don't drag the parachute too far down the concrete. Parachutes survive run after run on the salt because it's all nice and smooth and slippery. The abrasive surface of an RAF base is slightly more upsetting to the parachutes. We're just trying to extend their lives for the out to the end of the week. All of that worked really well. There's then, as you probably noticed, a short pause while we first of all give the car a quick check round, make sure that the hydrogen systems have purged, because of course hydrogen engines, having been full of hydrogen, at the point where I lift off and punch the parachute button, that triggers a state called end of run, which shuts the hydrogen valves, and then all the hydrogen in the system is then initially burned through the engines and then pumped through the engines to get rid of it. The last remaining bit lives in the crankcases, dry sump, but we still need to try and pump all of that through. And it's enough from that 180 mile an hour run, just the simple number of revolutions pumps the rest of the hydrogen clear. So we're down at 0 hydrogen everywhere in the system by the time the car stops, which is brilliant. We weren't sure that would work And when we did the modelling, we thought maybe actually the car is purging itself to a safe, in inverted commas, a hydrogen-free state, much better than we expected, which is brilliant news. There's then unbolting the parachute from the back of the car so that we can stow out the vehicle, turn the car with the world's biggest turning circle, 250 metres or whatever it is, a turning circle. So there's a huge series of arcs. It's the Austin Powers 19-point turn to get it round. Have it facing the other way, and then it's a push back here without the engines running, exactly as the push start you saw here to bring the car back. They push the car at the other end to about 55 miles an hour, and it arrives here still doing 50. There is so little drag in that car. We're all looking at, how is this possible? Where is this energy coming from? It just doesn't lose energy. It's a brilliant piece of technology. And as you can see, it's then easy just to coast it all the way up, park it next to the shed where the guys can work on it. So a hugely successful day. Thank you all very much for joining us to share that. Best run so far. You can see all the guys are excited, despite the fact they've been up most of the night fitting that lovely shiny yellow bodywork. So it's been a really brilliant day.